Hello, everyone. Welcome to our latest webinar, Transient Thermal Resistance, presented by Thermtest. I'm Angela, your moderator for today's session. Today, we are venturing into the revolutionary realm of thermal conductivity measurement, specifically focusing on adhesives and thin films. Adhesives and thin films. I can speak, I promise. We will explore a groundbreaking technique that effectively decouples the effects of thermal contact resistance, leading to more accurate results. Our speaker for today is the distinguished physicist at Thermtest, Ms. Renee Goodman. With her extensive background in the design and synthesis of semiconducting polymers for novel flexible electronics, she's made significant strides in the development and testing of thermal instruments. Towards the end of our webinar, we will have a question and answer session. Although this will occur towards the end, we invite you to type your questions into the chat box at any point during the webinar. Renee will address them during the Q&A portion. Without further ado, let's embark on this enlightening journey. Over to you, Renee.
Thanks, Angela. My name is Renee, and I'm a physicist at Thermtest. And today I will be talking to you about measuring the thermal resistance of thin films using a transient plane source. So a brief overview of today's presentation. So first I will introduce thin films and why we are interested in them from a thermal management perspective. Next, I will overview some of the existing methods for measuring thin films. Then introduce the technique that is the focus of today's presentation and a little bit of its theory. And then finally, I'll present some data and measurements, and we will wrap up with our Q&A portion.
So why are we interested in thin films and adhesives? Well, these materials are important in the thermal management of electronics, medical devices, and electrical vehicles, among many more things. And given these applications, we're primarily interested in measuring their thermal resistance and thermal conductivity. So these metrics will give us insight into things such as contact quality, intrinsic thermophysical properties, as well as bond line thickness performance. So currently, thin films are measured in a steady state, which involves setting up a temperature gradient, placing the sample between it, and allowing the whole system to come to equilibrium. Now, this process can take upwards of half an hour, sometimes as much as an hour, as the heat travels through the sample. And since the sample is in direct contact with our sensing materials, we need a reference test in order to account for that contact resistance. Furthermore, because we want to maintain this temperature gradient, these tests need to be conducted in an isolated thermal chamber. A common technique that is used during these measurements is that of layering. So layering just consists of stacking multiple pieces of our same sample in order to increase its total thickness. Sometimes in the case of steady state methods, this is up to 30 layers of our sample. And as described as in the standards, this is something that may be done in order to meet instrument set specifications or calibrations. And one of the key assumptions of this technique is that there is negligible contact between the layers of our film. Another thing that layering does is it improves the quality of our measurement by allowing us to mathematically isolate the contact resistance between our sample and the backing in the post-analysis. So one of the improvements that's been done to measure thin films on the steady state methods is the bulk thin film method based on the ISO. And this is done using a transient disk source. So because it's a transient source, essentially we can cut down on the time that the test actually takes, and we can do this test at room temperature. However, as you can see here, our sample is still in contact with the sensor directly, which means we still need a reference test. So this brings us to the key method of this presentation, which is the transient resistance of thermal films. The thermal resistance of thin films using a transient source. So this configuration is a one-dimensional configuration, and it starts with a thick steel rod. And then we place our thin film sample, and then on top of that, we place a thin steel slab, then our sensor, and then we're going to mirror the configuration on the other side. So one of the key differences here is the inclusion of this thin steel slab. And what this does is it decouples our sample from the sensor and essentially eliminates the need for a reference test because we no longer have a thermal contact directly between the sensor and our sample. We can partner this with the layering method in order to isolate the contact resistance that is left between the steel and the sample. So essentially what we're able to do is isolate the intrinsic thermal resistance of the film through one test. So to actually get this number, we use what's called thermal quadrupoles. And what these thermal quadrupoles are examining is the flux through any particular region, as well as the temperature at each boundary of the region. So as we add more regions, basically we add more quadrupoles, which represent this. And since our thin film is significantly thinner than both our steel pieces, we can essentially represent this purely as a resistance, which makes it easier to solve for. And then if we're looking at layering, as we add more layers of our thin film, the total thermal resistance will be linearly additive, which gives us a relationship between the total thickness of our sample and its intrinsic thermal resistance. So here we have an example measurement made on Teflon thin films. So the thin films are 85 microns thick each, and we tested 3 layers, so up to a total of 255 microns. We also put ethylene glycol between each layer, and this helps us adhere to the assumption that there's no contact resistance between the layers. So what we get from this data is, first of all, the slope represents the intrinsic thermal resistance of our material. So taking the inverse of this slope will give us the thermal conductivity. Secondly, we are able to get the contact resistance between the steel backing and our sample through the y-intercept. And again, this is a property that's of interest, particularly with coatings and adhesives, where we want to know the behavior of the contact between two materials. And if we look at the results of the thermal conductivity, we can see that those obtained using this transient method agree very well with the well-established values found for steady-state methods. Importantly, there are a couple of key confidence indicators we can use to establish more confidence in our results. The first one is the linear relationship between the thickness and the resistance. We want a high degree of linear correlation between the two, because this tells us we're truly looking at the intrinsic thermal resistance of our material and not any undesired surface morphology effects or anything like that, which may skew our results. The second one is during the transient measurement, we're able to measure the properties of the steel, namely the effusivity and the volumetric heat capacity. And what this does essentially is it serves as an indicator of the transient working properly. So in conclusion, this is a method that is far more convenient and uses less material than our steady state counterparts. And most importantly, it decouples the contact resistance between the sensor and the sample and eliminates the need for a reference test, which is something that we don't see in any other thin film method. Secondly, using the multi-layered technique, we can basically isolate the contact effects and examine those contact effects or simply the intrinsic effects independently if we want to. And lastly, we get excellent agreement between these values and those observed in the steady state methods. Thank you very much. I will now be happy to take any questions.
Thanks, Renee. I think we've got one question here. Would you be able to give us any real life examples of how this measurement impacts the way thin films are used in the real world?
Yes, that's a good question. One of the most common ones is through, for example, tapes, which are usually we need to examine them in situ, or we want to examine them in situ where they're directly adhered to the material we're interested in. So this method would allow us to investigate the thermal properties in situ, how they would be used, and look at things, both the thermal effect of the contact between the tape and the background, as well as the intrinsic materials of the tape itself.
Very interesting. Thank you.
Thank you.
Thank you, everyone, for attending our webinar on transient thermal resistance with Renee Goodman. Thanks, Renee, for taking the time out of your busy schedule to provide this educational opportunity to understand transient thermal resistance. Keep an eye on your inbox. We'll be sending out the webinar recording within the next few days. And if you have any further questions, please send us an email at marketing@thermtest.com, and a member of our team will gladly assist. I hope everyone has a wonderful day, and that concludes today's webinar.